Good morning, students. I welcome you all for the another session of this video lecture on RCC. In the previous class, we have studied the different limit states. Okay, how these limit states are applied. Then we have seen characteristic strength of materials. Then characteristic load. Then how to convert these into design loads and design strength using partial safety factors, that is gamma m, for the materials as well as for the loads. Now we'll start with another interesting sessions. So before going into the details of analysis of elements, we will going to see what are the assumptions, okay, in the limit state collapse. That is how using these assumptions we're going to use the limit state method for the design of elements. That is, we'll consider principles of limit states design and ultimate strength of reinforced concrete sections. So in that, first we'll see what are the different assumptions made in the limit state analysis or limit state method. So the first assumption is plane sections normal to the axis remain plane after bending. Now before loading, suppose if you take a beam example beam, before loading it will be straight, so there will be no deflection, no bending. So once the load comes on the beam will going to be deflect or it will going to bend slightly. So before loading, whatever the axes which are perpendicular to the plane, so even after bending they will going to remain perpendicular to the axis. That is, plane sections normal means perpendicular, plane sections perpendicular to the axis remains plane after bending. So before bending and even when the load comes after bending also, the plane sections will going to remain plane. Then second assumption, maximum strain in concrete. See, this is important. Maximum strain in concrete. When the concrete fails, okay, so there will be a strain, maximum strain, that is called maximum strain in concrete at the outermost compression fiber is taken as 0.0035 in bending. See, this is very important. Please remember, maximum strain. No, consider when the beam is subjected to loads, okay, when the load increases, okay, stresses and strain will going to increase, stress will going to increase, strain will going to increase up to a failure. So at the time of failure, the maximum strain in concrete at the outermost compression fiber is taken as 0.0035. So there is no unit because it is a strain has got no unit. So when the concrete fails, at that time the maximum strain in the concrete is 0.0035. Please remember this. Okay, so the third assumption, the relationship between the compressive stress distribution in concrete and the strain in concrete may be assumed to be rectangle, trapezoid, parabola, or any other shape which results in prediction of strength and substantial agreement with the test results. Means, if you draw the stress strain curve, the stress strain curve for concrete, so the compressive stress distribution in concrete and strain, so stress in concrete, strain in concrete, if you draw curve, then diagram, stress strain diagram, then this diagram may be taken as, it may be rectangle, it may be trapezoid or parabola or any other shape for the prediction of strength. Okay, for design purpose, the compressive strength of concrete in structure shall be assumed to be 0.67 times the characteristic strength. See, this is important again. What do you mean by this? For design purpose, so for designing of all the RCC elements, the compressive strength of concrete, alright, we're going to consider compressive strength of concrete shall be assumed to be 0.67 times of characteristic strength. What is this characteristic strength? FCK. In the previous article we have seen characteristic strength of concrete is denoted as FCK. For design purpose, we are going to multiply 0.67 times of FCK. The partial safety factor gamma m equal to 1.5 shall be adopted or applied in addition to this. So in design, what we are going to do? We are not going to consider the characteristic strength of concrete. So for that characteristic strength of concrete, we are going to multiply factor 0.67. So why this is multiplied, we are going to see next. Okay. So for characteristic strength, we are going to multiply 0.67. Then partial safety factor for concrete, already we have seen gamma m is equal to 1.5. This is also divided. So it is nothing but, so at the time of failure, compressive strength of concrete or compressive stress will be 0.67 into FCK divided by 1.5. That is gamma m will be divided. So this is the final compressive strength or compressive stress of concrete at the time of failure. So why this 0.67 factor is multiplied, we are going to see. So this is the third assumption. Then fourth assumption is the tensile strength of concrete is ignored. This is also important. The tensile strength of concrete is ignored. Now see, as you already known that concrete is very good in what? Compressive strength. It will going to take a maximum compressive strength. But when it comes to the tensile stress or tensile load, it will not going to take, because concrete is a brittle material. Okay, it will going to fail. It will going to take only compressive stresses, no tensile stresses. So that's why we consider the tensile strength of concrete is ignored. That will not be considered. So this tensile strength will be taken by steel. Okay, but concrete will not going to take any tensile stresses or tensile loads. This is another assumption. Next is the stress in the reinforcement. Okay, the stress in the steel bar are derived from representative stress strain curve for the type of steel used. So for this also, so for concrete we are going to consider 0.67 times, okay, divided by 1.5. That is for maximum compressive stress in concrete. Similarly, for maximum stress in steel can be found out by drawing stress strain curve for the type of steel used. So here also, for design purposes, the partial safety factor gamma m for steel is equal to 1.15. It is not 1.5. For concrete, partial safety factor is 1.5. For steel, we are using 1.15 shall be adopted. Okay, then the maximum strain in concrete, the maximum strain in the tensile reinforcement, okay, in the section at the time of failure shall not be less than. So when the steel fails, okay, the strain should not be less than, this formula, that is small e is strain. So strain, ultimate strain it is. U means ultimate strain in steel. Okay, small e indicates strain. U indicates ultimate, means at the maximum, at the time of failure. Ultimate strain in steel is equal to 0.87 Fy upon Es plus 0.002. Okay, this is the formula we are going to use to calculate maximum strain in the reinforcement, that is in steel bar. So ESU is equal to 0.87 Fy upon Es plus 0.002. Then what are these terms? ES, capital E indicates Young's modulus of steel. ES, Young's modulus of steel, and it is taken as 2 into 10 raised to 5 Newton per mm square. This is fixed. The Young's modulus of steel is 2 into 10 raised to 5 Newton per mm square. And Fy is characteristic strength of steel or yield strength of steel. So from this we can calculate what is the maximum strain in concrete will be considered. Okay. Next. Now we're going to see the stress strain relationship for concrete. This is for stress strain diagram for the concrete. So the code permits, which code? This is IS 456 2000. Okay, Indian Standard Code 456 2000. Code permits the use of any appropriate curve for relationship between the compressive stress and strain distribution in concrete. So now see, if you draw the strain in concrete, stress in concrete, if you draw stress strain diagram for the concrete, so we're going to get the curve like this. See, this is the first curve, this is the second curve, and this is the third curve. First we're going to get only one this, then we're going to convert this curve into second and third. Okay, now see, the compressive strength of concrete in the structure, compressive strength of concrete in the structure is assumed to be 0.67 FCK. In the previous article also we have seen that 0.67 times of FCK. Okay, so the compressive strength of concrete in the structure is assumed to be 0.67 FCK, that is curve number 2. See this curve number 2. So this is at the time of failure. What will be the compressive strength of concrete? It is 0.67 times of this FCK. FCK is characteristic strength. Okay. 0.67 factor. Why we have to multiply this 0.67 to this FCK? 0.67 FCK is introduced to account of difference in strength indicated by the cube test. Okay, now why this 0.67 is multiplied lesser than this FCK? So as you know, consider if the characteristic strength of concrete is M20. M20 grade concrete means it is FCK will be 20 Newton per mm square. So for design, we are not going to consider this 20. It will be reduced by a factor multiplying 0.6. So that is 0.6 into 20 Newton per mm square. Why this 0.6? Now this whatever the 20 you have got, this is 20 Newton per mm square, which is obtained in the laboratory test. When you consider the concrete cubes and if you test, it will going to give 20 Newton per mm square. But the same concrete when you want to use in the site conditions will be different. Okay, there are many variables, changes will going to take place. So if the concrete which gives 20 Newton per mm square in the laboratory test, it may not give 20 when the same concrete is used in the site. So reduction will be there. So that reduction is how much? 60%. Okay, that is 40% will be reduction. So 0.6 will be multiplied. Okay, 0.6 times of FCK. So that is, okay, the 0.67 factor is introduced, okay, to account for difference in strength indicated by cube test and the strength of concrete in the structure. So always in laboratory it will going to show higher values, but when you use the same concrete at the site, there will be some constraints will be there. Because of that, the strength will going to be always lesser. So lesser strength will be considered in the design. The initial portion of the curve is parabolic. Now see, the initial portion of the curve is parabolic up to what? 0.002 strain. Okay, so when the strain reaches in concrete 0.002, right, up to this it is parabolic shape. Then at a strain of 0.035, means this is the final strain. At the time of failure, strain in concrete is 0.0035. So at the time of failure, the strain in concrete is 0.0035. Okay, the initial portion of the curve is parabolic at a strain of 0.35. Okay, is reached when the concrete is said to have failed. So this is the, at the time of failure, the strain in concrete is 0.0035. 0.35, that is curve, is reached when the concrete is said to have failed. The design curve, that is curve number 3, curve number 3 is important. Okay, the curve, this curve is obtained by using a partial safety factor gamma m, that is 1.5. This is concrete, so gamma m will be used 1.5. Now see, this is the initial FCK will be higher, then factor we will going to multiply 0.6 into this FCK second curve, then the third curve which is used for the design, okay, 0.6 FCK divided by partial safety factor gamma m. So 0.67 FCK divided by gamma m for concrete is 1.5. So 0.67 divided by 1.5, it comes out 0.45 FCK. 0.45 FCK. So what is this? This will be the final compressive stress or compressive strength in the concrete. Okay, compressive strength or compressive stress at the time of failure is 0.45 times of characteristic strength. Okay, right. So this is important. Remember, at the time of failure, compressive stress or compressive strength of concrete will be 0.45 times of characteristic strength, that is FCK. So for design, this curve will be considered. So for design purpose, which is equal to 0.67 FCK divided by 1.5, that comes out 0.45 FCK. So therefore, maximum compressive stress, okay, at the time of failure, maximum compressive stress in the concrete is equal to 0.45 times of FCK. Okay, this 0.45 times of FCK. How this 0.45 FCK comes? FCK, then multiply factor 0.6, okay, because the test results in laboratory is different, inside condition is different, so that's why we are multiplying 0.6. Then again further this will be divided by partial safety factor gamma m. So finally maximum compressive stress in concrete is 0.45 FCK. Similarly, if you draw the stress strain curve for the steel bars, so there are two types of steels. One is this is a stress strain curve for mild steel. Mild steel means plain bars. Okay, then this is stress strain curve for HYSD bars, that is Fe415 steel. There are two types in this: Fe415 grade steel and Fe500 grade steel. So see, if you draw the stress strain curve, okay, strain in steel, strain in or stress in steel. This is stress strain curve for steel bars. This is a stress strain curve for the concrete. Okay. Similarly here, see the first curve will be what? Characteristic strength of steel, that is Fy. For steel we are considering this is Fy, and for concrete it is FCK. So characteristic strength of steel is Fy. Again this will be divided by 1.15. Here factor will not be multiplied, as like it is FCK, and here you are multiplying 0.6 for the concrete factor. Here we will not be going to multiply, because if you test the steel, right, if you test the steel in the laboratory also, and whatever the strength we are going to get in site also, it will be same, it will not be reduced. That's why here Fy is not multiplied factor here. So directly Fy divided by partial safety factor. Okay, partial safety factor. For steel it is how much? 1.15. For concrete it is 1.5, but for steel it is 1.15. So Fy divided by 1.15, we will going to get 0.87 Fy. Okay, 1 divided by 1.15, it is 0.87 Fy. What is this 0.87 Fy? At the time of failure, the strain, okay, the strain in steel will be, sorry, the stress in steel, the stress in steel will be 0.87 Fy. Just like this 0.45 FCK is the stress in concrete at the time of failure. So 0.87 Fy will be maximum stress in the steel bar at the time of failure. Okay, similarly this is for Fe415 or same for Fe500 grade steel. Okay, so the stress strain curve for mild steel and stress strain curve for Fe415 steel are shown in the figure. The modulus of elasticity of all type of reinforcing steel ES, capital ES is equal to 2 into 10 raised to 5 Newton per mm square, that is Young's modulus of steel. Also the stress strain relationship for steel in tension and compression is assumed to be same. For mild steel, the stress, see for this, for mild steel, the stress is proportional to strain up to yield point, up to here. Okay, so this curve will be strain, okay, that is straight, right? So stress will be same and strain will be same, means proportional to each other up to this point. And thereafter the strain increases. So after this, the strain will going to increases at constant stress. Stress will going to remain same now here. So strain will going to be increased. Okay, taken as constant stress. The design yield stress of steel is equal to Fy upon gamma m. See, characteristic strength of steel divided by partial safety factor Fy upon gamma m with a value of 1.15. This factor of safety or partial safety factor is 1.15 for gamma m. The design yield stress becomes 0.87 Fy. So this is the final stress in steel bar. At the time of failure, the final stress in steel bar is 0.87 Fy. For cold worked bars, that is for Fe415 grade steel and Fe500 grade steel, there is no definite yield point. So there, like this, there is no definite yield point. This will be curved. Okay, so hence yield stress is taken as 0.2% of proof stress. So remember here, what is the maximum stress in concrete? So maximum stress in concrete is 0.45 FCK. Maximum strain in concrete 0.0035. 0.0035 maximum strain in concrete at the time of failure. What is the maximum stress in concrete? 0.45 FCK. How this 0.45 you have got? FCK, then multiplied 0.6 factor, then this will be divided by partial safety factor 1.5 for concrete. We are going to get this is the maximum stress in concrete at the time of failure. Similarly, Fy, that is the characteristic strength of steel or yield strength of steel, this divided by partial safety factor 1.15. So we are going to get maximum stress in steel bar, maximum stress in steel bar 0.87 Fy. Okay, so these are the two important factors we're going to remember. So please go through this once again. Try to remember what are the important aspects what you have studied in this class. So if you have any doubt, please feel free to ask. Okay, so we're going to come up with the next session will be very important tomorrow. We're going to start with the analysis. Okay, analysis of beams. Okay, so don't forget to watch the videos. So thank you very much for attending the session. Thank you.